So we are going to cover two more topics today, and so one of these is basically estimating convective transfer coefficient for flow across banks of tubes. So this will be our next topic. So let's do that. So before we do any calculation, I would like you to visualize some of the possibilities here. So we have a fluid flowing in a cross flow geometry. And let's say if the fluid is cold, let's say this is the fluid is cold and the pipe carries hot fluid. Okay, so what's going to happen if this is inlet and if this is outlet, the temperature of the fluid that is flowing across the tube bank is going to change. So inlet temperature will be different from outlet temperature. So that is first observation. Okay. The second observation is, so depending on orientation of this tube bank, so they can be oriented in an aligned fashion, shown in figure A, or they can be oriented in staggered fashion, as shown in figure B. So if they are oriented in align versus staggered, the flow behavior will change. So flow behavior around each tube will be changed. So that is important to realize. So two things will change. So inlet and outlet temperature will change as the fluid passes from one row to another row. So we call this row 1, row 2, row 3. So the row number increases gradually. So we define velocity Vmax as follows. So it is inlet velocity corrected by this ratio. So this is the distance, center to center distance, minus this distance. So we are taking ratio of this distance divided by that distance, and that is the corrected velocity. Okay. For the case of staggered case, so we are correcting it by, again, this distance. We are dividing this distance by ST. ST is the diagonal distance here, so this distance, ST, and minus D, and then multiplied by 2, and this is the correction for staggered flow. So the Vmax, the maximum velocity, is corrected. As you can see, this area is larger than this area, so that means the velocity will increase. So this will be an increased velocity here. So we also mentioned the flow behavior will be slightly different. So in this case, when you have an aligned situation, the fluid in the around the first cylinder, just like we analyzed the flow around the cylinder, you have a laminar flow and then wake formation. This wake formation, after you have the wake formation, it's going to persist across the next sets of cylinder. So on the other hand, if you have staggered orientation, you start with laminar, and then you have wake formation with the turbulent flow, and then next one may still experience some laminar flow instead of going directly into wake formation. So in here, in configuration A, so after you reach the turbulent flow, it's going to continue turbulent, but you have also some regions that are not very well mixed, so that is another issue to think about. In general, heat transfer is related to the degree of mixing in flow. So basically you'll be mixing the cold zones and hot zones. The better mixing you have, the better heat transfer you'll experience. So how do we estimate the average convective transfer coefficient? So we have one equation that's called Zukaskas equation. So it is more complicated than other ones, so we have to consider several factors. But let's take a look at that. So this is average Nusselt number. It will allow us to calculate the average convective transfer coefficient for the tube bank. So for the Reynolds number, we'll be using Vmax. We just defined. So Vmax should come from velocity and then geometrical correction, based on aligned or staggered configuration. And then So we have Prandtl number and of course Reynolds number. The question is, at what point do you need to evaluate the properties? So the properties needs to be evaluated the arithmetic mean. So T inlet plus T outlet divided by 2. So this is T mean. Okay. So this is not T film. T film was T surface plus T infinity over 2. So you had a single object. So surface temperature here. And then you had T infinity. You are averaging across surface and T infinity. In here we have multiple tubes. So we have T inlet and that goes out T outlet. So we are not averaging between T inlet and T surface of single pipe. We are averaging between T inlet and T outlet. Okay, so this is the way we need to average temperature, and we need to evaluate the properties, all the properties except PRS at that temperature. Okay, and PRS means the surface temperature. So this is the surface temperature of the tube bank. Surface T of tube bank. Okay, and this equation is valid when the number of tube rows are more than 20. So we have row 1, row 2, row 20. So we need to have more than 20 rows to be able to use this equation. If we have less than 20, we need to use a correction, which I'm going to show you later. But at this point, remember this equation. If you want to use it in the current form, we have to have more than tube rows. Okay, not the number of tubes, but the number of tube rows needs to be greater than 20. So, and the coefficient C is tabulated here. So C and M actually, C and M. So it will depend on, so you need to first identify your configuration, whether you have a line or staggered configuration. And then you need to also look into the range of the Reynolds number based on Vmax. And then you read your C1 and M value. Okay. And if you have less than 20 rows, so you'll be using this correction factor called C2. So your Nusselt number, you calculate as if you have a Nusselt number, it's greater than 20, and then multiply it by C2. This is the correction factor, and it depends on the number of tube rows. So you basically, 20 means 1. So if you have 20 or more, you have 1. So you can interpolate between, let's say if you have 12, you interpolate between 10 and 13, between these two values to get the correction coefficient. And then you multiply your Nusselt number as if you calculate it with 20, and that's how you get the corrected Nusselt number. So if the outlet temperature unknown, so in most cases you will have a problem. Ti is known, T surface of the banks are known, T surface. So T surface, these will be known, but you will not know T outlet. In most cases, let's say you are trying to estimate what is the outlet temperature if you have 100 tubes within a system. Okay, so what do you need to do? So in this case, we'll be using this equation, and from this equation we'll be calculating T outlet. Okay, so T in is known, Ts is known. So D is the diameter of the tube, N is the total number of the tubes. Okay, this is the total number of the tubes. H bar is the average value, rho is the density of the fluid, V is the velocity, incoming velocity, and T is important, number of tubes in each row. So how many tubes we have in each row? So three tubes in one row. So we have 1, 2, 3, 4, 5, 6, row 1. So this is 6 tubes in one row. Okay. So ST is the spacing. We talk about in the diameter here. So ST is the spacing between these two, and CP is the heat capacity. So you can calculate T out here. However, you need to realize if you don't also know h bar, you need to do an iteration, okay? Iteration may be needed, because if h bar is not known, as we just talked about, and problem is h bar needs to be evaluated by evaluated at t mean. This is t in plus t out over 2. So what you may need to do in many cases, you need to estimate, you need to guess a t outlet temperature, and from the t outlet temperature you will find t mean, and from t mean you will find h bar, okay? And then you do a calculation here and find out your t out and compare t out found from this equation versus t out that you guessed, okay? So remember, this requires an iteration sometimes if h bar is not given. And if you know if you do know h bar, it is going to be just utilization of this equation. And if you like to calculate the heat transfer rate per unit length, so we need to use this equation. This is h bar times pi d, and in actually it is pi dl, but we are calculating per unit length. So h times pi d, this is area over length. And then delta T log mean is average temperature, logarithmic average. This is log average, okay? Since the temperature is, let's say, T in, T out, so T in will be different from T out. So there will be temperature difference between T in and out, and this will be gradually changing. So we cannot use T in, we cannot use T out, we need to use an average. For this particular system, when the log average gives you a more accurate result, and the way to calculate the log average is given here. So we have Ts, the surface temperature, Ts minus Ti. So this is delta T in at the inlet, delta T inlet. The delta T outlet is Ts minus T out. This is delta T out. So this is delta T in minus delta T out divided by log delta T in divided by delta T out. Okay? So we will talk about the derivation later on, but this is how you calculate the total heat transfer rate per unit length for the system of tube banks. And if you need to calculate the pressure drop, so what is delta P when there is a tube bank? This is important because you would like to know, let's say you are trying to select a pump for a heat exchanger. It has a tube bank inside, so how are you going to decide what power you need? So the idea here, so we have an empirical equation here. So the equation has two variables here. So F is the friction factor and chi is the correction factor. So, and you read these you read this from the chart, and L is the number of tube rows. So the number of tube rows, how many tube rows you have? 1 row, 2 tube row, row 1, 2 row. How many tube rows do you have? So row 2. So this is how we calculate the pressure drop. And rho times V square over 2 is actually has the units of pressure. So let's take a look at the friction factor. So it is fairly easy to read. So you calculate Reynolds number, okay? So, and after you have the Reynolds number, so you have the Reynolds number, and then you calculate PL. This is defined as SL over D, and PT is defined as ST over D. So what you do is you basically read your PL value, okay? And then from PL value you read the friction factor. And X, so chi actually, this is chi, Greek letter chi, the correction factor, you calculate this ratio, and from this ratio you read the chi value, and this is log scale, okay? So after you read these two values, you go back to this equation, and you can calculate the pressure drop. And if you have the staggered orientation, this was for the align case. This is aligned. For the staggered configuration, so we have a slightly different curve. And in this case, again, so the definitions are the same. PL and PT are defined in the same way. So this is how you calculate, how you read the friction factor. And the curve for chi is more complicated. And this is, you take the ratio of PT over PL.